think now we start off with the first, let's say the first paper session. So during this session, we will have three interesting presentations. For your information, each presentation will take about 20 minutes. And after that, we have 10 minutes for questions and answers. Of course, during the presentation, if you have a question, please feel free to already enter or raise your question in the chat session of chat part of this session. And of course, later on, there's the virtual world that you can also use to follow up these discussions if the Q&A session is too short. Okay, so as you can already see, the first presenter of today is Xia Wu of Accellera Labs, and she will be talking about portable stimuli. So Xia Wu, it's up to you.
Thank you. So hello, everybody. My name is Xia Wu. I'm a verification specialist from Accellera. Today, I'm going to present a paper with the name, Does it pay off to add portable stimulus layer on top of UVM IP block test bench? This paper investigates the effort to create a PSS-based solution on the traditional UVM test environment and how it contributes to improve the verification efficiency. We present 5 concrete challenges that we have experienced when creating a PSS model and propose solution to overcome or mitigate these challenges. This paper is based on an evaluation project we carried out in Ericsson Lund in 2019 with assistance from Cadence. Portable stimulus is in recent years becoming the emerging trend in functional verification world. Portable stimulus has shown its benefit of creating reusable stimulus and tests which are constraint randomized with the aim at faster functional coverage closure. By reusing the stimuli and the test case on different platforms, we also make sure that people across the team agree on the same requirement and test in a more uniform way. This creates a bridge across any target platform and is a key motivation of using PSS. Accellera System Initiatives announced the release of the portable test and stimulus standard on June 2018. The standard provides a language to describe the test requirement and content in a highly abstract way. The standard supports both PSS-DSL standard input format and C++. It provides the control of activities with loop, branch, parallelism, etc. Also, it introduced concepts like resource, data flow object, constraint, and more to allow the correct and automated creation of a scenario from a user's partial configuration. Due to the abstract and implementation agnostic nature of the PSS language, early adoptions are mostly done and evaluated on the system-level test bench. The connectivity test, which verifies the data flow between different subsystems, is the main target. Block-level test bench, with a lot of low-level typing and implementation details, are rarely chosen as the target for PSS deployment. When we look through the recent publications and articles, we also don't find much on this subject. We think that from the reusability point of view, it makes sense to start from block-level test bench because the subsystem and the system test were mostly likely to be built on a subset from the existing block-level PSS implementations. And it allows maximal vertical reuse and improve the verification readiness in other platforms. Our motivation is to find out what the effort and challenge is to migrate the UVM block-level test bench into PSS-based solution. Through this project, we also want to investigate the tool support for PSS. Now, the benefit for PSS is that it helps us reaching faster functional coverage closure by aligning stimulus generation with coverage goals. We reach coverage goals with fewer iterations because we don't waste any simulation through repetitions. For a project with different parameter setup, this is especially useful because it simplifies the verification process by putting all parameter setup into the same regression. Using PSS model, we only generate tests which target directly the coverage goal. This reduces tests in the regression a lot. In the brute force UVM only regression without seed ranking, we need approximately 1,000 seed and 24 hours of machine time, depending on how many parameter set we have to get full functional coverage. For PSS-based solution, the number of tests is reduced to about 50%, since it is doing the seed ranking upfront. We got 100% functional coverage in the early verification stage, and this reduced the license usage and the machine power for running regressions. PSS promotes reusability and will, in the long term, reduce redundant test development time in subsystem and full system test bench. Also, the visual representation of the test scenario improves communication and aligns the understanding in the test requirement and strategies across different teams. This evaluation project is based on the PSS tool from Cadence called Perspec. It is a modeling tool which can be used in the batch or GUI mode. Perspec enables PSS model development, simplifies scenario creation, scenario randomization, target code generation, and abstract debugging. Perspec supports PSS-DSL input format and C++ from the official PSS LRM, as well as their own system-level notation language as a supplement. This figure shows how PSS and UVM are interfaced. We can see that PSS is a layer on top of UVM and is in a different language domain. What Perspec does is to bridge this part to interface with each other. It provides the framework to link the PSS implementation to the standard UVM test bench. We start with implementing a model in the PSS-DSL language. Then we use the Perspec to translate the PSS model into scenario code in C++. The scenario code controls the synchronization and timing of the underlying UVM sequence by DPI calls. Then we manually create a Perspec test, which is a UVM test object in system Verilog. This initiates all the thread defined in the C code. The Perspec test itself is only served as an initiator to the whole process, and therefore it can be shared by all the PSS test cases that are created in this way. So we have one Perspec test and a lot of scenario code representing different test cases. And the low-level bus transactions, they are still taken care of by the UVM sequences. The Perspec test itself is a UVM test object, so it can coexist with the existing UVM test. Therefore, it does not introduce any backward compatibility issue. Our target DUT is a highly configurable filter chain system, which can be viewed as a series of filter engine blocks processing data independently or in-chain. The number of the filter chain blocks are generics set in compile time. The way these blocks are cascaded are configurable in runtime, so they can be running independently by taking this red path, or in-chain by taking the blue path, or in a mixed way. The existing UVM test bench verifies around 10 different generics combinations for the DUT, and for each combination, there are different runtime configurations. Therefore, a lot of test cases are needed in the regression to close coverage. Collecting functional coverage and code coverage is usually tedious work. The complexity level of the UVM sequence is high. It requires correct timing and stimuli, and that is also one of the reasons we chose this IP block as our target. And here is an example of the PSS model for the test we created. What we see here is a scenario generated by the Perspec tool from our PSS model. And it is a visualization of the model of the test case. And what it does is that it configures 6 filter engines in parallel and randomizes them. Then it schedules data stimuli sequence and send them to the DUT. The data stimuli are sent in a certain order in serial or in parallel, according to the test requirement. The test is built up from a sequence of atomic actions. Each of them is representing by this green round box. Some of the actions, they are the randomization of the configuration, while others has an implementation of the UVM sequence. The test case itself is also an action. It's called a compound action. So in the paper, we discussed 5 concrete challenges that we met when we implement our PSS-based solution. So here is a list of these challenges. First is the compile time parameter. We found that coding many parameter set for the same PSS model can be made easy by the Cadence SLN language. Second, runtime configuration. We show how to create the model in layer and distributing the complexity into each layer. Inheritance. It is a powerful methodology to create test case, but it can be further improved for code reuse. Partial description. We think that successful solving is heavily dependent on good constraint sets and coding style. And last, semantic equivalence. We found that one should be very aware of the semantic inequivalence between the PSS model and the UVM tests. So let's start with the first one, compile time parameters. An important reason we use the PSS is to verify the IP block with all valid combination of generics. Our target DUT is also highly generic. It has several different block parameter setup. The UVM test bench has a system Verilog package with fdiff around each set of the parameter. The regression runs all the tests on all the setups. So to migrate this into PSS, the PSS model also needs to be generic so that it can generate test case based on each parameter set. However, to put all the parameter set together and select a set from them is not easy to do in the PSS-DSL language. It requires some manual repetition of code. Cadence SLN language, however, it supports a table construct, which is a macro-like mechanism to capture code repetition. It reads the parameter from a CSV file into the PSS model. So let's take a look of it, an example here. So all the parameter set, they are defined in a CSV file, and each row is a set of parameter used by the DUT and the test bench. In the SLN file, we use the CSV to table command to read out a parameter set, which the name is equal to setup, which is defined here as the setup default, and which is the first row in this table in the CSV file. And then these parameters can be passed on as individual constants to the PSS model. So in this example, one can define all the needed parameter in the same table. And by defining only one parameter, which is this setup, the parameter set is selected and applied in the PSS model. And without this, it is still possible to do the manual coding to the generics in the PSS model. But when we hit the large number of generics combinations, we found that this table construct, it simplifies the parameter set selection and avoid repetition in coding the model. So we consider it a very useful add-on to the existing PSS-DSL specification. So the second item is runtime configuration. So another challenge we have is to cover all the dynamic configuration of the DUT. In our case, one must cover all the possible scenario of the chaining of the filter engines. And we show some of these configuration in the figure. So what we have to do is to cover all the possible starting point and end point of a chain, as well as all the chain size. When the number of the filter engine blocks increase, the permutation of different chains also increase significantly. In the existing UVM test bench, we define the constraints of valid chain and rely on the randomization to generate all the possible chain combinations. By ranking the seed, we found a set of optimal scenarios which contribute to achieve the coverage goal. And let's take a look at how to do this in the PSS. So how to model this complicated runtime configuration? We define this randomization of each filter engine block as an action called channel. The randomization should be one action per filter engine, and this is to keep the test bench scalable. The action, it needs to know the starting point of a chain, the current index, and the size of the chain. Besides, it also has some design-specific variables, such as this MPSEG in use, which should be the same throughout the chain. These variables are directly linked to the cover point. Besides that, a lock should be created to ensure a unique ID on each channel action. Then we create a data object, data T. This is a stream object. Stream objects, they represent transient data or control exchanged between actions during concurrent activities, and they represent data item flow or message notification exchange. In our model, we use the stream object as the constraints between the actions. For example, the first engine need to inform the second filter engine that I am the first in the chain and you are the second in the chain. The chain size is 3 and MPSEG in use is 5, and so on. In this way, we create a virtual chain of the filter engine blocks by utilizing the stream object to pass the constraints. This example is an interesting use case to show how flexible the language and the model can be to generate useful scenarios. And here is the code implementation of the channel action and the data T stream. So when the base action is created, we extend the channel action according to its role in the chain to add another complexity level to the base action. There is a variable in the action, which is called channel role. It is representing where the filter block is in the chain. The role can be master, which means it's the first in the chain, middle, or last. And then we extend the channel action to channel master, channel middle, or channel last action. And what we show here on the right side is the implementation of the channel middle. We see that channel middle, it has both input and output data. And the first constraint here is to help it to connect to the channel action whose index is 1 less than its own. And the rest of this constraint is to extract the information like starting point or chain size from the input data. And these constraints are to pass the information to the output data. So in a similar way, we can also implement the channel master who has only the output and channel last who has only the input. After that, we create a third complexity level, which is the test case. The test case constrains the way these filter blocks are cascaded. For a normal cascade test with 6 filter engine blocks, we constrain the channel 0 to be channel master, and then channel 5 to be channel last. And the other channels, they are constraint randomized by its previous channel. When the constraints are set in the test case, then we can use the solver to generate the scenario for us. And this example is a scenario of a cascaded filter chain generated by the Perspect solver, with the first 4 filter engines in one chain and the last 2 filter engines in another chain. So when the solver fills each channel with all the possible roles, we achieve the coverage in all the possible cascading options. And this is basically how we model the runtime configuration in different layers and distribute the complexity in each layer. The third is the inheritance. In PSS, it is also possible to use inheritance. So in PSS, it's also possible to use the inheritance to simplify the coding. It is supported by the PSS-LRM. We have also shown in the dynamic configuration that one can extend the base action to create a new action. The test case is the highest layer in the PSS model, and it is also defined in action. It is possible to extend the PSS test case just like the UVM test. This example shows a test case which is extended to a specific test. The sequence of activities, they can be shared by different tests, and the difference is in the constraint. So in this way, it is easy to create tests in a short time, and it's therefore important to plan a good structure before starting to implement the PSS model. For tests with more details in the control part, we need to extend PSS model to add complexity into it. The basic approach is to create an action for a UVM sequence. The complexity in the low-level transaction should be kept in the UVM sequence. The controlling of the sequence, it should be leveraged into the PSS model. Adding this abstract layer on top of UVM gave us a better graphic-based control over sequence, and the portability is also much improved. One limitation to the reusability here is the PSS model usually have many control knobs. The control knobs are passed by the DPI function variables. And since there is no support in polymorphism in System Verilog, we had repetitive DPI functions which start the same UVM sequence, but with different number of randomized variables. A possible solution is to pass the control parameters in a struct, which is proposed by Cadence. And we have not yet tested this. Okay, now the partial description. PSS, it supports abstract partial description. It means that the model does not need to specify all the steps, but it can instead rely on the data flow and the solver to get a complete test scenario. And this approach works as we shown in the dynamic configuration. But when we have multiple parallel test process running, with each of them passing a different configuration from action to action, we start to see constraint solver problems. We think that the success of abstract partial configuration is highly dependent on the coding style. One test case we encountered is a power-saving test case. In this test, we configured a number of filter engines, and then we send out stimuli several times. And between each time stimuli is sent, we turn on and off the power control, and then check if the output is still the same as what we expected. The main problem here is that we have 6 channel actions, and with each of them representing a filter engine and randomize a variable called MPSEC in use. This variable is needed in the action run 1, run 2, and run 3. And the variable should only be passed to the run actions, which belongs to its own channel number. In the PSS actions, we define input and output data, but it is completely depending on the solver to connect the data to the correct subsequent actions. We found that in a highly parallelized system, if without many detailed constraints, the solver has difficulty to connect 2 actions correctly so that it will generate invalid or unwanted scenarios. And if we don't want to sacrifice the flexibility that partial configuration provides, we must find a balance between the partial and the fixed configuration. And our solution here is to group these actions into a compound action, which is also shown in the code here. We use a lock to ensure each compound action related to one and only one channel. And then we define the MPSEC in use inside this compound action. So you can argue if it is conceptually correct to have this sort of a global variable in the PSS model. And we must say that it is a workaround to get the solver to do the correct thing. And it could be that the newer version of the tool is more mature to handle partial description in similar cases. So last item is the semantics in equivalence. We know that it is essential that when migrating test case to PSS, the same semantics of the existing UVM test should be kept. But this is not always the case when we migrate system Verilog cases to PSS. An example shown here is the reconfiguration test case. What this test does is to configure the DUT and then send the data to the stimuli. And then it configure the DUT again and send the data stimuli out again. So this is a very typical reconfiguration test. When we created the initial PSS model for this test, we found that it is inequivalent to the existing UVM test. As you can see here, the test result shows that the first configuration, it has the correct randomization with the constraint that we defined. But for the second time configuration, the constraints seem to be missing, and we got this very large and incorrect number as the randomization results. This initial PSS model, it produced semantics which did not match the existing semantics. And we found that two problems should be taken care of. First is that the synchronization between the C and the system Verilog for this specific test should be extended. This is because our synchronization is event trigger based, and we cannot simply just put a loop around the actions. We need to create new event to synchronize the C and the system Verilog. Second,
sorry to interrupt you, but we only have 3 minutes left, so I'm not sure if you can go to the conclusions and still have some time to answer the questions.
Yeah, okay, no problem. So yeah, so let's conclude and wrap up. So we found that it is realistic to add a portable stimulus layer to an UVM IP level test bench with reasonable effort. And the effort is paid off by improved verification efficiency, faster functional coverage closure, and reduced test in the regression. PSS promotes reusability and potentially reduce redundant test development time in other target platforms. Therefore, we consider it a very useful add-on to the existing dynamic verification techniques. So yeah, that is the end of my presentation.
Okay.
Thank you everybody for attending. And let's see, do we have any questions?
Yeah, so if you open the chat box, you can see the questions. So one of the first questions from Bas. He's talking about parallelism. If the question is how to conserve PSS parallelism if we have to go through the DPI-C interface, and do you need to do something special in the UVM test level environment to enable this?
Yes, so when we use the Perspec tool, we found that all the parallelism is handled in the C scenario code. So the Perspec test is initiating all these parallel threads in the C code. So basically, that is how the parallelism is handled by the Perspec framework. So no, I don't think something special need to be taken care of on the UVM level. Okay, so next question, I don't know if we have time. Random stimulus has the advantage that we find additional fault in configuration that are not modeled in the coverage model. When we use target stimulus that is related to the coverage model, how can we ensure that we do not lose this benefit? So I think the first thing is that when we define the coverage model, we should be certain that these are the things that we test, and additional things that is not covered by the coverage model, they should not be in the spec, right? So we should deliver the product which is according to the spec. And it is correct that the more tests we do, the better. And I think by using the PSS, we reach the coverage closure faster than the traditional constraint randomized way, so that we have more time to maybe define in our coverage model what else we want to test. So that is one of the benefits I can see by using the PSS.